transportation and outside engineering, more than 40 of them that engage with us in different topics. So CATS was launched in 2017. It was established by a seed fund from the Dean of Engineering at the University of Toronto. And then we went out there seeking partners, and we secured a very decent partnership group, including City of Toronto and the Region of York, and with funding from NSERC. The vision overall is to focus on disruptive technologies. Like everything is becoming automated, green, and shared. You can call them, for instance, the ACEs, automated, connected, green, and shared. And we want to understand as transportation professionals, what would the impact be on our cities, positive or negative? We don't really work on the automation technology itself. We're civil engineers. But if you can imagine, for instance, if the Greater Toronto and Hamilton area, you wake up tomorrow and all cars are automated and connected and shared, and how would the city look like, or how the region would look like? Is it a boon or boondoggle? We ask these questions. So we focus, for instance, on the impact of automation and green powertrain, innovative data collections, innovative multimodality, like first mile, last mile, and demand responsive transit, etc. Innovative goods movement like crowd shipping. And then we also try to understand how all these technologies that kind of show up all of a sudden in the market, how would that change travel behavior, including the emerging mobility as a service and transportation as a service that the entire domain is going towards. And of course, we're guided by the core triple bottom line sustainability principles, including economic sustainability, social sustainability, and environmental sustainability. You can think of the work we do as having three themes. Theme number one, that was primarily the focus of the first 5 years of CATS, which is quantifying transformation. If we just watch the emergence and proliferation of these technologies, what would happen? And of course, there are positive aspects of this and potentially very negative aspects of this. And then we monitor what happens to our cities in terms of sustainability principles. And then theme number two, which is what's coming next, is we try to say, okay, if transformation is leading us in certain directions, and if we find out that those directions are not really desirable, how can we steer it back in a positive direction? So learning from the research before it actually becomes a reality. Like we all, for instance, know what happened with the car itself 100 years ago. It showed up, and then all of a sudden suburbs happened, and urban sprawl happened, and massive congestion happened. So can we think ahead of the curve this time? So CATS 1 has finished, and you will see examples of the research that has been done today. And CATS Next, which is the next 5 years, we are trying to move closer to field deployment. Like if you're familiar with technology readiness levels, we are done, or we think we're done with the basic research, and we want to drill down, getting closer and closer to technology readiness level 9 and field operation testing and field deployment, as you will see in a second, and potentially using also the campus around us as a living lab or a test bed. We structure ourselves along 5 verticals. The 5 verticals, one of them is traffic AI. I'm leading this. Like for instance, smart traffic lights, self-learning traffic lights, adaptive freeway control, and so on. And then there's smart transit solutions. I'll give you examples of that. And then automated goods delivery. Transit solutions is led by Professor Amer Shalaby, and freight and logistics and automated goods delivery is led by Professor Matthew Rorda. And then the climate positive, all the environmental impacts are led by Professor Marianne Hatsopoulou. And math and human behavior is led by Professor Habib and Professor Eric Miller is participating in both the climate positive and travel behavior. To give you quick examples, like for instance, we're known for the eMarlin adaptive traffic control system that you will hear about in the next presentation. The question simply, can traffic lights learn to be smart? And we have a long history of research in that space. And most recently, we've been fortunate to work with the City of Toronto to deploy this. Currently is under construction, deploy this system on Shepherd between Don Mills and the 404. We're hoping to evaluate in Q1 of next year. In terms of automated vehicle delivery, Matt Rorda does, for instance, research on Follow Me robot, how it interacts with people and pedestrians, both in simulations and hopefully in real life as well. Now, there are real life deployments that we can learn from, analyze how they interacted with their environment and impacted city streets. In terms of climate positive, this is Marianne Hatsopoulos' field. She models emissions out of vehicles and how they are concentrated, for instance, in certain areas and around certain corridors. Often people who are less financially affluent are getting higher exposure to emissions. And she has this urban scanner vehicle that can drive around, take videos, and measure emissions in real time. And now she's working on reducing the size of this bulky infrastructure to be deployable on fleets like taxis and Ubers and whatnot, in order to maximize the sensing and the management of environmental impacts of transportation. In terms of smart transit solutions, for example, dynamic bus lanes and adaptive bus lanes, for instance, interaction between buses as they approach traffic light, announcing that they are coming, and the traffic light would adapt itself. And then also interact with the bus's back, saying, for instance, if you adjust your speed in a certain way, you will make it to green, you will reduce emissions and reduce battery consumptions or fuel consumption, and so on. And then finally, like mobility tools in terms of travel behavior, with all these technologies popping up, who wants to buy them? And how people would adjust their travel behavior in response of the availability of such tools. Like for instance, if you have an automated vehicle on your driveway, all of a sudden this vehicle can do multiple trips in the day, so can generate more demand, as an example. Or you might not own one at all because you can call one with your smartphone that would come and pick you up, whether it's like a private sector company or whatnot. So we need to understand how people would receive the technologies, interact with the technology, and change their behavior. So all these verticals will be addressed deeper in the next 5 years. And then cutting across as a horizontal, there are two research horizontals. One of them is digital twinning, because everything requires modeling, but not just modeling in the sense of having a simulation model, but digital twinning implies that you have a model that is driven by real data flows, coming up with decision-making and pushing the decision-making back in the field. So how do we do this for adaptive control, for transit systems, and so on? And AI, of course, everything nowadays is AI, and you will see many, many examples today of that. In terms of partners, again, it's the University of Toronto, U3, Transportation Research Institute, the City of Toronto, that's I'm talking about the next 5 years, Region of York, the TTC, Esri Canada, and a proposal just went yesterday to NSERC, if successful, then will be decently funded for the coming number of years. So this is a very quick introduction to to CATS, and now we can start the program. Karim, if you could switch the presentations, please. Our first session is dedicated to traffic AI. And we have 4 presentations in the session. The first presenter will talk about the eMarlin X adaptive traffic signal control system. The developer or the speaker or the developer of this system is Dr. Xiaoyu Wang. Actually, the whole session that this morning will be people who just finished their PhDs recently at the University of Toronto in the past year, with the exception of Dr. Ilya Smirnov, who was a research associate and then now is at the City of Toronto. So Dr. Xiaoyu Wang is a postdoctoral fellow at the University of Toronto at the current time. He received his PhD in civil engineering from the University of Toronto under my supervision and co-supervision of Scott Saner, Professor Scott Saner from Mechanical and Industrial Engineering. His expertise include intelligent transmission systems, artificial intelligence, AI foundation models, reinforcement learning, and control systems. He was the prime force behind the eMarlin system over the past 5 years or so. And he's currently also collaborating with the City of Toronto, with Dr. Ilya Smirnov, on integrating the system into in the field and deploying that system, which would be the focus of the next presentation. So without further ado, Xiaoyu, it's all yours.
Thank you, Professor. Thank you, Professor Abdelhai, for briefly introducing me. And I will add a few sentences on my background. So my background, as Professor mentioned, was on control science and machine learning, AI. And I transferred to this domain of transportation and civil engineering since I joined the U of T 6.5 years ago as a PhD student. So as an outcomer, like I was thinking that, okay, it should be easy. I just adopt some methodology, some algorithms into this field, voila, it should work. But this whole group spent 5 years to develop the whole series of eMarlin algorithms. And finally, during my postdoc period, we can push it towards the street. So it was a laboratory-born product, but now it's kind of industry-grade system that's ready to deploy. So what's the gap between the research and the field deployment? That will be our focus of today's topic. So our research purely focuses on adaptive signal control, and we can generalize it to different traffic management domains, but today we just focus on the signal lights. And many people, when I was talking to them that I'm doing this research, they will complain to me that sometimes when I'm driving towards a traffic light, I see green light. Well, there's not really much vehicles in the other approaches. So the plan is stupid. And is there any solution? Yes, that's why this concept of adaptive traffic signal control was developed. So there should be a bunch of related methodologies in the field to address this kind of issue. You have more sensors, you have more concrete controllers compared to the pre-timed timing plan strategies few decades before. We can combine those sensors and the computer to support really quick real-time decisions such that a traffic light can allow this vehicle to pass through very rapidly. So is there a case that the traffic light still insists to not allowing it to pass through? And that's a kind of real-world question, but it actually inherits a gap between the research and the real world. So look at this example. It's a synthetic experiment we designed to better, where's my mouse? Oh, okay. To better control the scenario to show what's happening. So you have a platoon coming from the west, going to the east, and a single vehicle going towards the north. And initially, the right-hand side traffic light was having green on the eastbound. Well, it sees the northbound vehicle is coming, so it releases it. But there's a blackout period. You have this minimum green time, you have red time, you have yellow intermediate time. So the signal light can't flap the signals just in a second. So whenever it changes the signal to northbound, it holds the eastbound platoon. So from a system optimistic perspective, what's the most ideal would be that we just hold the northbound vehicle for 2-3 seconds and rather let the eastbound platoon going through. But usually speaking, that's a better global optimum. But usually speaking, if you're just doing a naive adaptive signal control, your agent can't do the right-hand side strategy as you expect. So where's the gap? There's a gap between what's happening in the field and what you read from your sensors. We call this a gap between the state and the observation. So first, you have cameras, you have loop detectors, maybe you have LiDAR or radar mounted on the poles around the intersection, but they always have detection range limit, right? You can put a high cost to cover the entire street, but then information sharing, how to address those information is another issue. So whatever, there's a gap in the detection range. And even if the vehicle is inside the detection range, you have another type of lack of sensing. Only a snapshot can be captured by any type of sensor. For loop detectors, you just know there is or not a vehicle. For radars, similarly, for cameras, if you have a good enough camera, you know the position, and you can kind of reference what is the speed and the acceleration rate with your algorithms. So break the previous example down to this diagram, we see that when the northbound vehicle is entering the detection range of the right-hand side intersection, the platoon can be hidden from the hidden range. And it makes a locally optimal decision to let the northbound vehicle going through, but that's not a global optimum. So during my PhD period, there are several rounds of the iteration on the algorithms, but we finally reached a stable version called eMarlin Plus. It is a distributed reinforcement learning-based signal controller. So it's designed to support decentralized decision-making. So yes, you can have a centralized center to aggregate data, to do the monitoring, but for making decisions, centralized center is not necessary. And it's designed to support lightweight communication, real-time decision-making. It makes decisions in second-by-second level. So in the very beginning page I showed, if there's really a single vehicle coming, eMarlin-X can actually let it going through. And even in this more slightly complicated kind of green wave emerging example or coordination example, eMarlin-X can also find global optimum by purely learning from the experiences. So with that being said, there's a gap being addressed between the theory and the application research. There's another gap between the application research to the application. And that's why we collaborate closely with the City of Toronto to deploy these 4 intersections with our improved, we call eMarlin-X system to the field. So what I was showing is that, okay, in the synthetic network, there are 2 intersections, a few vehicles. We can move those a few vehicles pretty fluently. That's still pretty simple, right? The real world is much more complex than what we designed in a synthetic scenario. And this is the traffic demand spatial and temporal distribution around this Shepherd and the Highway 404 corridor area. And we see it's clear that it's very unevenly distributed, either in the space or in the time. And if we go to the traditional control systems, what is the control paradigm? We can pre-calibrate different timing plans according to the time of the day, right? And we give it a different name. We call it specialist. So for eMarlin Plus or eMarlin-X, we can also train different agents corresponding to a different time of the day to reflect the traffic pattern, not exactly in real time, but still corresponding to different periods. So we call that a set of specialist agents. We can have an AM peak agent, a PM peak agent, and a few more. Is there another way? Imagine that there is a single plan that is conditioned on the traffic condition. So this single policy or the traffic plan or the control strategy, depends on how you call it, it can actually adapt seamlessly over the entire day or entire week, entire year, right? There's no weekday plan. There's no like special event specific plan. We don't yet know if it's possible, but let's just call it a robust agent for now. So this single agent can first read what's on the street, and it gets an idea what is the demand profile look like, and reacts to the specific traffic conditions. This is a little bit constrained in this scenario. Another example we always like to give is that you're a player. It's an example given by a professor, so I find it very vivid. You're a player. You can play any games with a racket. So you can play table tennis, you can play tennis. The setting is somehow similar, but not exactly the same. You can have 2 specialist players, one playing table tennis, one playing tennis. But if you give the table tennis player a racket from the tennis game, it may not perform properly. So that's called a set of specialist agents. And human are actually pretty adaptive. You can learn different games. You can play table tennis while playing tennis. So we call that a robust agent. You can adapt yourself to different rules in different similar games. And yeah, that sounds good, but it's not critical, right? You can still have a set of agents, but not why. But why not? So we actually trained. Where's my? Sorry, the animation is sort of cracked. We trained a set of Oracle level specialists in this 3 demand periods. And we can see that, okay, specialists are doing good. Can we generalize them? They're reducing a specific percentage of delay time corresponding to the transweave pre-timed system. And if we generalize it to the scenarios it never seen before, it can perform poorly. For example, this green bar, it is the off-peak specialist. Because during the off-peak, the traffic demand is light, so it can't generalize properly to different demand. And in real time, you can say there's a different specific period, but you can't say light vehicles, so light demands always present in that off-peak. You may experience high demand in off-peak. So that's why we say specialist approaches is not ideal. It can be rigid. When should we shift the plan? And it can be intractable. If there are tons of demand profiles, how do you manage that? So that's the reason why we finally concluded our research with this eMartinX robust system. So there's a single robust plan. It adapts seamlessly to different traffic contexts, even for perturbated or unseen demands. So there's no plan shifting at all. You can think of it comes up with a plan in every second. And it abides strictly by the policy regulations. It's, again, another kind of minor gap between the lab environment to the real world. You may notice that there's a, for example, leading pedestrian interval being spread over the entire Toronto city. That's kind of one of the constraints. You have that constraint, you have less time to manipulate. So that's a really hard challenge for our learning-based system. And I'll skip this theoretical stuff. Just very high level is that our backbone is called eMartin Transformer, a version of eMartinX. What Transformer is, it is the backbone of modern large models. You're actually using transformers if you're using GPTs. So as rule of thumb is very strong. So it gives us the capability to address the partial observability as I illustrated in the previous animation. It also gives us better generalizability, better robustness. You can faithfully train the single agent on different scenarios. And there are a series of tricks to, you have a good agent, it can learn many things, but you need to properly train it such that it actually understands what you're expecting, right? So there's another list of tricks we need to perform to push the eMartin Plus towards eMartinX robust. And training is a little bit hardcore. So what about evaluation? How do we know that our agent is robust enough? We designed a set of scenarios. So as you've seen before, we got real-world demand scenarios from three times of the day, three periods. That's what the real data we have. But we can always play with those data and get some unseen scenarios to the agent, right? So the first test is just on these three base demands. But you can scale it, you can do a linear combination, you can activate different pedestrian arrival patterns, basically meaning if the pedestrian pushing the button, the minimum green time for the specific phase getting longer, so your agent gets lesser time to play with. That makes the scenario harder. You can also do perturbation to the demands. You can also combine some tricks in the previous test to derive the following tests. All these tests are covering a pretty wide range of either interpolation or even extrapolation. For example, if you scale a peak demand even higher, the agent never seen it before, right? So we're evaluating this agent across 75 scenarios, unseen scenarios, and run through over 1,000 scenarios, replications, to see if it's really adaptive. And the evaluation result is straightforward. It's doing good. And what are these metrics? First one is we call stop delay, or it's the dwell time. It counts the time the vehicle is stopped in front of the signal line. And TTD is total travel time. This is the emission saving. So that's why we call it a leaderboard. Oh, and by the way, the baseline is used still the Transsuite, and it's a TOD-based plan. So we calculate the distance from a specific scenario to one of the three TOD demand, and we ultimately assign the best close it plan to the specific scenario, and that's how we evaluate the spaceline. So overall, we're providing real-time adaptation and seamless adaptation and coordination by this eMarlin X system. And facing to the field, eMarlin Transformer Robust Agent can save about 20 to 30% of the delay over this semi-actuated Transsuite system. And moreover, it's in one positive role. It's a robust agent that perform good against any variations. And that's why it is ideal for deployment. Thank you for bearing with me. Any questions?
Great, thank you very much, Xiaoyu. If you have any questions, we can take a couple of questions.
Yes, sir.
Yes, please.
This is
Transsuite, we call it a semi-actuated plan. It's not an algorithm. It's basically a management system. So what's inside Transsuite is that you have a timing card. You have different plans for M peak, PM peak, off peak, weekend, and maybe for one closure. And the Transsuite system will pick the timing plan corresponding to the time of day.
It's pre-timed system, like not adapted.
Still, it's a little bit actuated based on the loop detectors.
But in the current deployment, which you'll hear about next,
Oh, yeah.
we'll be comparing to an adaptive system that is currently in the field, which is SCADS.
The SCADS from Australia.
So what we noticed that on average, we save about 20-30% delay, but I wanted to explain what that is. Like 20% or 30% less delay doesn't mean that 30% of the cars will disappear. It means that if you, for instance, you stop at a traffic light for 1.5 minutes, it could be down to 1 minute. So if I save you half a minute at a traffic light and you go through 20 of these, then we can save you about 10 minutes on a commute trip. So this is what delay reduction means. Usually the savings in delay are much larger during the shoulders and the off-peak, like midday. During the peak, the system is like constrained, so the percentage savings is less. So it could be overall about 20-30% or so. Any other questions? Great. If not,
can you hear me?
Thank you,
Hello?
Xiaoyu.
Sir, can you hear me? Hello.
So now we move on.
Can you please type your question in the chat box?
So you can think of Xiaoyu's work as the theoretical foundation. That's his PhD and some of his postdoc work. But now how can we take the output of a thesis, a couple of 100 pages document, and a lot of code that is running on U of T servers, quite capable servers, and you put that on the street. There are so many differences here, what kind of detectors you use, what kind of computing you use, how you integrate all the components together and make sure that they work in the field. And for this, our next presenter is Dr. Ilya Smirnov, that he will talk about the details of the ongoing field deployment, including hardware communications, system integration, and installations. Dr. Smirnov is currently a project lead at the City of Toronto. He's currently working on real-world evaluation of the eMarlin Adaptive Traffic Signal Control system, and he's interested in applying reinforcement learning from AI, from artificial intelligence, to traffic management problems in general, including traffic signal control, ramp metering, freeway control and ramp metering, perimeter control, i.e. regional traffic signal control, and autonomous driving. Fun fact, his PhD is in mathematics, is in algebraic geometry, and he still retains strong interest in the subject. And his favorite space is moduli of vector bundles on a curve. Don't ask me what that means. Ask him. So without further ado, I turn it over to Ilya. Please take it away.
Yes. Hello. Can you hear me?
We can hear you
can't
online.
hear you.
Yeah. So I'm unmuted.
Can you hear me?
I can hear you. Test.
I think he's just switching audio on his device.
I am not.
Yeah, let's try it now. Can you hear me? Ilya, can you hear me?
Hello. Yes, I can hear you.
Okay, wait, I still can't hear you. Okay. All these seconds. Yeah, well,
Previous.
Yeah, we have it here in the chat box, Ilya.
Yeah, but I can't. I can't do the presentation in the chat box. Hello. Can you hear me now?
Yes.
Yeah.
We're just
So
waiting for them to switch audio
yes,
to the
this
speakers in the room.
sounds worth. Yeah.
yeah, Ilya, can you hear me now?
I can hear you. Can you hear me?
Yes, we can hear you.
Okay. Thank you. Yeah, so I want to apologize for not being there. Something came up with actually the construction that I'm going to speak about, and scheduling is difficult, so I'll need to right after this go play around with the cameras, try to adjust something about the cameras. So I'll have to present online. But right, so the presentation is about the current deployment, the test evaluation of the eMarlin system, and how what steps were needed to be taken to get it actually running in the field. So the problem statement is that, okay, so we have this algorithm. It's been evaluated thoroughly in simulation, and we actually need to connect it to the traffic light and run the traffic light. And the components of that is that the eMarlin implementation needs to support stage-based operations based on taking a decision each second, and the decision each second is either to stay in the current phase, which is called also extend the current stage, or change to one of the possible next stages. And because we're going to be interfacing with a traffic signal controller, which operates based on the NEMA, Turing standard, not all possible sequences of phases are permitted. So what we've been doing for eMarlin is to translate it to the language we've been using, is just to diagram every possible sequence of stages. Like for example, here for an intersection of two arterial roads, you have a very familiar operation, semi-actuated operation where left arrows are actuated. And based on presence in the detection zone on the left side, you can either one or both of the left arrows is either served or not. And so there are several possible sequences of stages, and that's what's possible for eMarlin to do. But what we need to do is, given after computing the eMarlin decision, extend, or change to implement that in on the actual traffic light. Okay, in addition, we need detection, and what we assumed during the research is that we'll have vehicle counts and counts of queued vehicles bent by lane. So for each lane, you have the number of vehicles in that lane and the number of stopped vehicles or queued vehicles, which means speed below a certain threshold, 2 meters per second, also in that lane. So, and in addition, as was explained before, it helps to have information sharing or optimization data sharing between neighbors to address some of the detection limitations. So that needs to be implemented in some way to exchange this information. So this is these are the components that need to be implemented in the system. And so we need to interface with existing infrastructure, and so that requires having a working knowledge of several component systems. And that's, I think, the difficult part here is that even though you're not inventing something new, you need to have a good knowledge in order to be able to troubleshoot and have confidence in that your implementation will do what you expect. So, and because different systems accumulate, it can get a little bit heavy. So this is just, I think, a more general pattern of bringing research technologies into the field and interfacing with existing infrastructure. So another theme is that following established standards, like several I'll mention, makes the solution transferable to other systems that follow standards. So this is, I think, very useful to do in order to have a system that doesn't only work on the particular set of hardware you have, but might generalize to other similar hardware. And if some creativity may be required to get around additional constraints imposed by the existing infrastructure, or if you can't do it, then you need to integrate those constraints into your problem and work with them in order to have a good representation of what you'll see in the field. These are kind of general themes for the talk, and the remainder will be quite specific to the traffic lights, but maybe if I give a specific kind of map for what the traffic light case is, you can see how it might, some of these things might generalize to your particular problem. All right, so how does traffic light actually controlled? So it's a useful picture of all the technology at a typical intersection from the York region. And what I focus on here is that around in the neighborhood of each intersection, there's a cabinet, a metal kind of shelf, closed shelf, enclosed space that's called the traffic signal cabinet. And that holds all the hardware and connections, connecting cables that actually run the bulbs on the signal heads. All right, so if you open it up, it looks a little bit like this. And I want to point out a few of the components inside. What is usually the system called actuated signal controller, which is the red big box here, or City also uses Econolite, which are blue boxes. And about as with the same proportion as the peak. This actually stores the real-time signal plans that we were talking about, the time of day plans, and interfaces with the detectors, so it receives calls from the detectors, and it puts out voltage calls to the load switches. So these load switches on the bottom are actually transform the voltage and actually light up the bulb. So you can't quite see the cabling at the bottom, but that goes out to the red, yellow, blue, green bulbs. So this bottom part is what actually activates the light, but the red part is the control. And there's also another component in the cabinet, which is called the malfunction management unit, which tracks that you don't serve conflicting movements at the same time. It tracks certain voltage characteristics like voltage jumps and so on. And in case something goes wrong, it puts the intersectional flash. So that's a separate component for redundancy. And finally, the Marlin, the adaptive signal control system, is running on a separate computer, which is another component in the cabinet. It's a rugged computer that it meets the thermal requirements stated by NEMA, it can work because it's an outside box. So you need to support operation during cold weather, during hot weather. From -34 to +74 is the range. It's fanless, so there's no worry about fans breaking and the computer overheating for that reason. And it supplies PoE to the cabinet. So we have a distributed system. So the decision is local at each intersection. You can have, as mentioned, a monitoring system or remote access. And for example, if you want to synchronize the time on each between intersections, you also need an external server, but the actual decisions run independently on an edge computer placed in each cabinet. Right, so this is the existing infrastructure in the cabinet, logical infrastructure. I talked a little bit about the components that go into the cabinet in terms of the physical hardware, but logically they're all connected to each other through what's called an SDLC bus. And SDLC is kind of an old communications protocol from IBM originally, I believe, and it's used throughout North America for communications between different components inside the traffic cabinet. And the ASC is the actuated signal controller box that was mentioned before, the red box. And so it places like a frame through this SDLC bus to the bus interface unit. It's called Terminal Facilities Bus Interface Unit to actually light up the traffic light. And it also, through the same communication channel as the SDLC bus, gets calls from the detectors. And MMU is also connected through the bus, so it can monitor the communication going on between the different components. And here on the top is just a little bit of an idea of how messages look like on the bus. So you have a template opening flag that you can recognize easily in terms of bits, the address, destination address of the message, and then just information and error checking. And so the question is now how to get from the eMarlin computer to the traffic light, to actually turn on the traffic light. And there are two main options. One is actually connect to the SDLC bus and communicate with everything as another component on the bus. A little bit difficulty with that is that the actual physical interface is not so standard. It's somewhat like an RS-232 port, but has a different number of pins. Pin out is also kind of unusual. So if there's not really, you would have to have, it's a separate, kind of electrical engineering problem to actually make an interface from a typical computer to the SDLC bus. So instead of that, the design right now is to connect the eMarlin computer through Ethernet local area network and NTCAP 1202 protocol to the controller, the red box in the cabinet. And then instead of the controller being the driver of the system, now you're overriding the controller, the traffic signal controller, by your decisions coming from the computer. So, and that's kind of the architectural decision made for the current evaluation deployment. I'm missing a lot of details exactly how to do this. So basically, the traffic signal controller is placed in the system free through NTCAP, and all the phases are placed on hold. And when you want to do an extend action, you don't do anything. You just wait for a second. But if you want to do a change action, change to a different stage, then you do a force off through NTCAP in the traffic signal controller. And that way you can actually implement, because the controllers are in free, there's no external force offs coming from the controller that's trying, and then if you place your phases on hold, basically you have complete flexibility on how long you serve those phases for. So this way you can implement your decisions made by the eMarlin system second to second to light up, to actually get them implemented from the traffic light. Okay, so that's the traffic light part. The detection part is that in this field, because of this logical infrastructure, that assumes that the calls coming from the detectors are relatively simple, meaning it's either 0 or 1, like a loop detector. Either a vehicle is present inside the loop or not. And if the presence is detected, then you can actually or extend a particular because of the pressure, and it's now a lot of cities are transitioning to non-intrusive detection, like radar detection or video camera detection. But everything in the field that uses SDLC tends to also be based on just directly translating the loop. So there is a detection zone, and it's either 0 or 1 in terms of presence, and it either makes a call to the controller or not. And this breaks some of our research assumptions we made when we were doing the research, where we had a more detailed representation of the neighborhood of the intersection in terms of seeing queue counts and vehicle counts over longer distance in the vicinity of the intersection. So what we ended up deciding is to, instead of buying detectors that are built specifically for SDLC, go a little bit outside of the field and get edge IP cameras that do AI on-device analytics, image segmentation, and classification. These cameras are looking to get into the traffic domain, at least the traffic monitoring. So they're trained specifically to classify traffic objects like into classes like buses, vehicles, motorcycles, and so on. And what these cameras do, they do computations on device, and they emit the locations, estimated locations of and speeds of each object that they detect, as well as the class, as a separate stream of text. And so this is much more detailed information than just presence within a certain detection zone. And this now you can implement counts from this data. It's actually more detailed data than human counts. But these cameras don't have SDLC supports, as I was mentioning before. So if you want to integrate them into this infrastructure in the cabinet, you go through the Marlin computer. So that's a relatively heavy integration problem, where now you need to learn how to stream from these cameras and get the data, parse the data, process the data, and so on. So this is a way to, as I was mentioning, so I'm not using now, or our project, the Marlin project, is not using a lot of the infrastructure that exists in the cabinet. That's in terms of detector, bus interface units, and detector calls. All of that is removed and replaced by information coming from the edge cameras to the Marlin computer. So it's not using SDLC anymore. So this is an example where your research assumptions made during the project don't quite fit with what's available in the field. So you need to maybe have another solution, be a little bit, find out a little bit creative, find another solution. And so just an example, so here are not very busy, but estimated geolocations of different objects. So each dot is a detected vehicle here, and it's fairly clean detection in terms of geolocation of objects. The white dot is the camera location. So. And then we have one camera for each approach. Finally, I'm running a little bit late, so I'll just mention quickly that for message passing between different intersections, we use the existing city infrastructure as well, where each cabinet is connected with each other on a private network provided by Telecom, Bell and Telus. And so we use that same infrastructure. It's despite being cellular, it's actually Internet Protocol based. So it's an private IP network, but it's based on LTE. And so this allows. So I wrote RTP real-time transfer protocol based protocol for information sharing between neighboring intersections through these cellular modem. So that also, I'm leveraging existing infrastructure. A lot of cities will have fiber optic cables connecting the intersections, which is nicer, but because the Marlin is relatively light in terms of message sharing requirements, it's only a few kilobytes per second. it can be supported by even the LTE network as well, no problem. Okay, so maybe I'll go over again what maybe the higher level points are, is that yes, the interfacing with existing infrastructure involves it starts involving lots of different existing systems that you need to spend a lot of time to learn well in order to have some confidence that they will work. So here I'm using cellular for communication, sensors, and the controller. Yeah, so but in the end, it works. So, and I'm using existing established standards like NTCA P1202 for the traffic signal controllers. Because I'm only using the MIP that's described in the NTCP standard, it actually does work with different controllers. So same implementation works with both PIC and Econolite. You do need to program PIC and Econolite differently, but okay. And for the camera, I'm using the ONVIF, which is also a standard for IP streaming cameras. It's a whole suite of protocols, including RTP, RTSP, RTCP, HTTP, but it's all standard. And so for ONVIF compliant cameras, it will transfer. So for instance, if I want to use Bosch or Axis or Avilion or another manufacturer or another supplier, I can change. It's not tied to a particular camera necessarily. Although, of course, each camera will have its own quirks, so you need to take that into account as well. And if your research assumptions were broken during, you can get often you can get around it with some creativity. But if not, like if you need a cycle to implement cycle bounds or LPI or pedestrian actuations, all of that needs to go into the actual problem statement if you want to get a realistic picture from your simulation. Okay, so sorry for going a bit over time.
Thank you, Ilya. Any questions for Ilya? Ilya, I'm wondering if you have a sample video from our cameras in the field that you can share. Is it handy or?
No, it's not handy, but yeah, I don't have it right away. Well, hold on, maybe give me a minute.
Okay, so what the status of the deployment at the moment is that the cameras are installed and we're getting the video streams and testing the detections. And then we've done the so-called hardware in the loop testing where you make sure, for instance, that the computer is talking to the controller, is talking to all the other components, and you test that in a simulation environment still, but the simulator in this case is just acting like the real world. So we made sure that all the components are working together. Currently, once the computer is ready, which is what Ilya is working on, then we can turn on the system and start evaluating. So by evaluating is that you have the video streams coming in. You can calculate the delays, for example, how many vehicles are queued, what the average speed is, and so on. And then you can compare whatever you want. So, for example, you could say currently there is the SCAT system working. Then from the video data, you can estimate how much delay there is in terms of stop delay and average speeds and whatnot, and then remove that and turn on eMarlin and do exactly the same thing again, and then compare. Compare saying, for instance, that one system is 10% better than the other system or 20% or whatever the number is. And we're also doing some regression analysis to make sure that, like, for example, if you test one system on a bad day and you test the other system on a good day, it so happened randomly that it's a good day, then one system might look shinier than the other, but it's totally by chance because you just lucked out and had a good day. So we make the performance assistant conditioned on the inputs. So in other words, how much traffic is getting into the system becomes an input to the system, and then therefore the delay would be conditioned on that input. So we can compare apples to apples at the end of the day. So I think I'll turn it back to you, Ilya, to kind of talk to this is the current installation on Shepherd and the detection system. So go ahead, Ilya.
Right. So these are videos I'm collecting there'll be a lot of videos. So this is not the highest quality available from the camera, but for purposes of having visible storage size, it's relatively low resolution. But you can see the point here is that the red dots are placed where the camera detects a vehicle, a car. And you can see it does fairly well in terms of even when relatively high occlusion, partial occlusion. It does, I would say, well, in terms of separating the vehicles and locating them with a fairly good detection. So these cameras, you're able to choose the lens for the camera. So we chose a telephoto lens with relatively high optical zoom in order to increase the detection distance as much as we could for the camera. And it's a relatively high mount height. Yeah, so it's an example. I think, yeah, it does relatively well.
You can also see the vehicles leaving on the other side of the road. So, which means that if your queue lengths are too long beyond the camera range, you can see it from both sides. So you can see it front facing, measure, let's say 150 meters. And then from the other intersection, you can see another 100 meters. So this way you can complement the detection state of the system. And then each intersection also transmits the metadata to the neighboring intersection. This is what Xiaoyu was talking about, the partial observability, that we're trying to see as much as humanly possible using the current detection so the decision-making would be as accurate as possible. Okay, thank you very much, Ilya. So stay tuned. Maybe by April, we will have comparative results and be able to tell which system is performing better. So one question back there. It will definitely affect how much you see. And in this case, like it's not going to fail catastrophically, but the decision making will be less accurate. Okay, so moving on. Now we're going to switch gears. Still traffic, still AI and reinforcement learning, but we'll switch to two different things. Number one, freeways, not traffic lights. And number two, what if the freeway is dominated by autonomous vehicles? So the questions become, can the autonomous cars drive themselves? That's number one. Can they cooperate with each other? That's number two. And number three, can they also anticipate upcoming congestion? So there is some cooperation between the vehicles and the state of the infrastructure. So for instance, if autonomous cars know that you're approaching a bottleneck and this bottleneck is congested, what do they do in order to improve traffic overall? So this would be the PhD of Dr. Tianyu Shi, who just graduated a few months ago from U of T as well, under my supervision. And Tianyu, before his PhD from the University of Toronto, had a Master of Engineering from McGill and a Bachelor of Engineering from Beijing Institute of Technology. He conducted research internships at UC Berkeley, University of California, Berkeley, and Montreal Institute for Learning Algorithms. His research focuses on reinforcement learning, multi-agent systems, and large language model agents. And he's going to talk about essentially his entire PhD in 20 minutes on cooperative multi-agent reinforcement learning framework for concurrent, microscopic, safe, efficient, and comfortable autonomous driving with a layer on congestion management. So can you, without further ado, please go ahead.
Thanks for Professor Bahar's introduction. And today I will talk about my research on multi-agent RL framework for safe, efficient, comfortable autonomous driving and macroscopic congestion management in freeways. So firstly, freeway congestion is a critical global issue with economic impact exceeding 11 billion annually in regions like Toronto, highlighting the needs for smarter traffic solutions. So in my research, we aim to bridge the gap between microscopic driving task and macroscopic traffic system performance. At the microscopic level, vehicles must complete their driving task safely, efficiently, and comfortably. From macro level, we care about metrics such as total outflow, average travel time, and land speed harmonization. So in other words, how well the overall traffic system operates. Our approach builds driving models that improve individual vehicle behavior while ensuring that those local actions align with system-wide objectives. This is done through cooperative and scalable reinforcement learning. So, firstly, at the micro level, existing models often suffer from conservative gaps, lack of speed regulation, fragmented line change logic, and discomfort due to high jerk. We propose the Sequem model and the Sequem 2D models to address those by using reinforcement learning to learn adaptive at headways, embedded speed control in rewards, unifying the line changes and jointly optimize safety, efficiency, and comfort, outperforming both human-like and rule-based models. So at the macroscopic level, traditional model often fall short due to selfish behavior, lack of coordination, infrastructure dependency, and neglect of system-wide impact. So our proposed approach addresses with a cooperative policy that consider vehicle interactions and multi-agent framework for decentralized coordination. And also we propose the micro-macro integration to align local behavior with global traffic efficiency, and infrastructure-free control relying only on CAV observations. So unlike next, maybe Omar will present the ramp metering approach. Our method achieve more scalable and adaptive coordination, and we only focusing on using vehicle level control instead of infrastructure level control. So this roadmap summarizes the whole evolution of the Sequem model families. We begin with Sequem, which focus on longitudinal control, unifying safe, efficient comfort through safe speed regulation. And then we propose the Sequem 2D model, which extends the agent to include line changing decision, supporting both discretionary and mandatory line changes, mandatory manuals. And next, we propose the cooperative Sequem 2D model. It introduces cooperative behavior between agents with two key variants. One is we assume a fixed cooperation factor
across all agents and use a local bubble level scanning mechanism for coordination. And next, we introduce dynamic cooperation, which allows the agents to adjust the cooperation factors based on the speed gap between fast and slow lanes, promoting adaptive interactions. And finally, we propose the cooperative Sequem 2D MM. This model builds on this by connecting micro-level agent behavior with macro-level traffic efficiency through bi-level optimization and a macro-aware micro cooperation factor in enabling the system to infer and respond to overall traffic conditions. So firstly, we will talk about the Sequem model. This highlights the fundamental trade-off. Shorter headways boost efficiency, while longer headways preserve safety. Fixed gap are either unsafe or inefficient. And we propose the Sequem model to address this by introducing dynamic headways, which can adjust based on vehicle speed and acceleration to adaptively shorten gaps when safe guarantee collision-free movement using analytical constraints and ultimately maximize flow without compromising safety. So to deal with the safe and efficient conflict, so we propose this equation to ensure follower can stop safely if the leader brakes, considering speeds, braking capacity, and reaction time. And to maximize the flow, the model keeps the gap as shorter as safe possible, resulting in a speed-dependent adaptive headway. So this leads to a variable target gap based on maximum safe speed. And this slide shows our Sequem model setup. The agent is an autonomous vehicle follow a human driver in single lane loop, and the state include speed, spacing, acceleration, and speed limits. The AV controls acceleration, and the reward encourage both smoothness and speed tracking for efficient, comfortable driving. The motivation of this form of reward is to penalize difference between target and actual speed and penalize sudden changes in acceleration. Next, this is the result. We can see that it's better than other baselines in terms of average time gap and average jerk. Also, we evaluate the model in emergent braking scenario. Sequem also outperform prior conforming models by avoiding collisions and minimizing jerk, achieving both safety and smoothness. And next slide, we present the Sequem 2D model, an extension of Sequem previous Sequem model to handle the lane changes with safety constraints. On the left is the model workflow. The agents receive observations, take an action through policy pi, and the action is then adjusted to meet safety constraints, limiting lane change direction and acceleration to ensure safe behavior. On the right, we show a highway merging example. The Eagle vehicle decides whether it's safe to merge based on available safe gaps. The reward function covers 4 aspects: efficiency for the longitudinal progress, and discretionary lane change efficiency for opportunistic merge, and mandatory lane change efficiency for planned exit, and comfort for smooth and non-aggressive driving. So we can look at the results. Across all tested scenarios, Sequem 2D consistently outperform other methods in key metrics such as safety, efficiency, and comfort. And in the bypassing scenario, it maintains safe and smooth performance across varying traffic densities. In the emergent braking scenarios, it avoids crashes and ensure comfortable actions. And in the merging scenario, it enables successful merge while maintaining high throughput. Overall, we can conclude that Sequem 2D achieved a strong balance between realistic decision making and robust performance under challenging traffic conditions. And the next step, we propose the cooperative version of Sequem 2D. This figure shows three driving behaviors. Firstly, it's a selfish one. It focuses only on the ego vehicle's goal. And the courteous one, it avoids disturbing others but lacks true coordination. And for cooperative one, it actively collaborates with surrounding vehicles to achieve better overall outcomes. And our goal is to move forward from individual or passive behavior and enable real cooperation among agents. So this slide shows that cooperative Sequem 2D control loop in a merging scenario. Each agent observes nearby vehicles and output actions, which are filtered by the safe constraints. We test the two cooperation settings. One is fixed cooperation is equally considered selfish and neighbors, and the dynamic cooperation is adjusted based on speed difference for more flexible coordination. And the reward balance ego performance with neighborhood level cooperation to ensure both individual and system performance. To ensure safe merging behavior, cooperation Sequem 2D use a dynamic scan range that adjusts based on worst case safe gap, considering vehicle speed and braking. The scan range is set as the larger of 50 meter or the computed safe gap, and is applied to both state and reward. When there's no leader vehicle, such as at the end of the ramp, we treat the lane end as a virtual obstacle to trigger safe braking. And this plot also shows that our method adjusts scan range effectively under different traffic demands. We then set the traffic demand profile near Sequem's theoretical capacity, and to test how the models can perform under saturated conditions and safe car following limits. So we can see that for Sequem 2D and cooperative Sequem 2D, it maintains high bottleneck flow, and it outperforms Sumo default model and showing better headway control. And with fixed cooperation factor, we can see that ramp vehicle merge more easily through mainline flow drops. Though mainline flow drops slightly, revealing a trade-off between merge across merge access and throughput. And we can see that dynamic cooperation briefly slows faster than vehicles to allow merging from this figure, and then it recovers the flow. Despite outflow losses, it achieves the best microscopic performance, showing it focus on balancing both mainline and merge line driving performance. So we can see there is still improvement area in previous models. So we proposed cooperative Sequem 2D MM guided by 4 research questions. One is how can we embed system-wide goals such as outflow and line balance into local agent decisions. And we use a hierarchical optimization approach. And also, how can agent adapt their behavior in response to changing traffic? We design dynamic cooperation mechanism guided by macro signals. And thirdly, how do we infer global traffic patterns from local observations? we introduce a Bayesian method to reconstruct the macro states from local scan data. And lastly, how does our agent-based method compare to traditional approaches? We test the performance across outflow, line usage, and coordination quality under varying demands. So this slide shows our hierarchical control framework with two levels. One is from the macro level. Agents adjust the cooperation factors using loop detector data to maximize outflow and balancing line speeds. And from micro level, it updates every time step. Each agent use local observation to optimize safe, efficient comfort through both selfish and cooperative behavior. So this shows how the whole optimization framework goes through. So here we also show that we could transform the local row occupancy reading into a smooth macro occupancy map by aggregating data over time. This provides a richer view of traffic density across the entire segment. And we further show that CNN-based encoding pipeline to infer the macro level traffic states from local scan data. And I remember I emphasized in the beginning, this is a vehicle level control framework and it's infrastructure free. So that we can utilize the measured sensor data to infer global compact macro features for downstream optimization. So next we formalize the whole cooperative Sequem 2D MM infer framework. This based on the previous two modules, we could remove the need for loop detectors by inferring macro traffic states from the local observations using CNNs, and it compared to the earlier versions, it's now infrastructure free and enable easier deployment, and it's more adaptive with fine-grained real-time traffic context. These inferred macro goals are used to dynamically adjust the agent reward for better coordination and efficiency. So this figure evaluates cooperative Sequem 2D MM under full demand. From the results, we can see that it can maintain most stable and highest outflow, and it improves ramp merging success rate, especially thanks to the macro-guided dynamic cooperation, and it balances mainline and ramp flow better than baselines. Lastly, it achieves higher flow even under high occupancy, indicating efficient capacity usage. Finally, this table shows the cooperative Sequem 2D MM version outperform all baselines across all demand levels. At full demand, it achieves lowest total travel time, best micro score, and most balanced line speed. Even under lighter traffic, it stays top performing. It's showing strong generalization without infrastructure. Its overall macro-aware cooperation with state influence boosts both individual and system level performance. So this slide finally summarizes the key contribution of my previous work from Sequem model to Sequem 2D, and then to Sequem 2D cooperative version of Sequem 2D model. Firstly, Sequem model focus on analytical safe carpooling models, and is provably avoiding crashes while optimizing comfort and speed tracking. Sequem 2D extends this to a full line changing framework, covering both discretionary and mandatory maneuvers, while balancing safe, efficient comfort. And also cooperative sequence, it introduced local multi-agent cooperation for merging using shared reward and dynamic scan range. This enables smooth and efficient merging under mid-demand traffic without infrastructure dependency. And finally, cooperative sequence 2D MM integrates macro-level coordination and micro-level control. It leverages the macro-state inference framework and bi-level optimization to improve bottleneck traffic flow, line harmonization, and overall system efficiency, making it the most comprehensive model in my previous research. So that concludes all my previous work. Thanks for listening, and please ask me any questions.
Thank you very much, Tianyu. Excuse me. Any questions for Tianyu? If you are driving a newer car, like for instance, I don't know, Tesla, Mercedes, Lexus, and whatnot, it has such self-driving capability where the car uses adaptive control to control longitudinally, but they are also capable of lane changing. But the question is how much space they leave in front of them. So if the gap is too large, then the overall traffic efficiency is low, meaning that if we all drive these cars, we'll be in deep trouble. So the question is how to kind of make the platoon as compact as possible while maintaining a guarantee on safety so you would not collide in the vehicle ahead. And all of this, as cars learn how to collaborate with each other, how they also manage traffic. And all of this without sensors, meaning that the sensors are in the vehicles, so there are no sensors on the infrastructure, and they are aware of upcoming congestion, and they kind of drive themselves with an eye on the macroscopic traffic behavior. So that's Tianyu's PhD thesis. Thank you very much, Tianyu. We move on to the last presentation in the morning session. Still traffic and still self-learning control, but the lens this time is not on the traffic performance in terms of delays and speeds and so on, but rather on the impact on the environment. So the hypothesis here is that if we adaptively control traffic, does that make the environment better? So we have the last presentation on environmental impacts of adaptive traffic signal control. The presenter, Dr. Omar Al-Samadisi, couldn't make it today. He has a conflict, but he did this work collaboratively with Dr. Xiaoyu Wang, whom I introduced earlier, who did the eMarlin platform. So let me introduce quickly Dr. Omar Al-Samadisi. When he did this work, he was a postdoctoral fellow here. He finished his PhD again in the last year or so, and then did some postdoc under my supervision. Now he's working outside, but his work with us focused on developing control strategies for freeways under both human driving, so controlling freeways, for instance, with ramp metering, and also under autonomous driving, similar to what we've just discussed. So with that, I turn it over to Xiaoyu to take over and show us the environmental impacts.
Thank you again, Professor. I'm back again. So in the last talk, I was introducing this eMarlin family of algorithms, and I was saying that it was designed to address the traffic signal control problem, where you can fairly confident to extend it to different other traffic management scenarios. And in this talk, you will see another scenario in parallel. It's called the ramp metering control. And the two set of algorithms share the same core, the mathematical core behind it. But because the dynamics is different and the control strategy are different. For example, in signal control, we do second by second, but for ramp metering control, you're more focusing on macroscopic metrics. For example, the flow on the freeway. So it has a slightly different mathematical background and slightly different agent design, but under the hood, it's always distributed reinforcement learning, and there's not significant differences between the methodologies. So in this specific talk, we'll talk about the side effect of optimizing traffic flow, either in the local road network or on the highway lanes. And what are the side effects? It's effects on emission and environmental impacts. So why would it be concerning is that, I will go, because we're behind the schedule, I will go quickly in this talk. So most of the people might be aware of this right-hand side chart. It says within either the world or Canada, the second large sector contributing the greenhouse emission is the transportation. Right here, it dips down because 2020 there was a pandemic around the world, and if we go back to half century ago and track the history of the CO2 emission and the concentration rate, it keeps increase very steeply. And governments around the world, including Canada, has paid a lot of attention to this phenomena. And there are some effects from different perspectives. So for example, in this study, it shows that VKT is the vehicle kilometers traveled. It means across the time period from 2004 to 2016, we see that there's no significant dropping in vehicle kilometers traveled. But if you go to emissions in this toxic emissions or the PM 2.5 emissions, they actually all goes down. It means the regulation on maybe the fuel standards and the vehicle manufacturing standards are altogether contributing to this reduction in the emission and the concentration, either greenhouse gas or pollutants. But is that enough? How should I hide? No. Yes. So is that enough? Although it has been decreasing, but if we look at the NO2, this toxic emission, its concentration rate across the Greater Toronto area, we can see that what WHO suggested is a standard of 5 ppb, and across the Greater Toronto area is far beyond 5. Most of the Greater Ontario area is above this WHO suggested standard. And what's the potential directions of further decreasing these emissions? Policymakers are certainly paying attention to different fields, but as transportation researchers, think about what is the most severe scenario when the vehicles will produce emissions. Idling, congestions, right? When vehicles are congested in a platoon, either on the freeway or in front of an intersection, it generates more emission. Also, if the vehicle is in a stop and go behavior, it accelerates and decelerates. That's something more than greenhouse gas emissions, because there are tire that called? Sorry. Brake and tire in stop and go behavior will generate more this, for example, nitrogen dioxide or PM 2.5. So let's see if we address the traffic behavior, giving more smooth platonings on the surface road or the highway. Can we get a better future in terms of environmental impacts? So the methodology is that we pick a emission model. There are actually more availabilities, but this could be one of the selected models. And yeah, this is the detail of the model. There are different hyperparameters for different types of cars and different pollutant types. So we run the entire simulation with this emission model equipped, either with RAM meter control for highway or signal light control for road surface, for road networks. And also in the previous slides, I was showing the emission was decreasing, but there's another detail saying that although the private vehicles, small cars are traveling more, higher kilometers, but they're actually contributing much lesser emissions. So when we're modeling the highway stretch and the surface network, we'll also pay attention to the split between light-duty vehicles and trucks, according to some public available data set. And the same network here for surface road, and another simulated network for the QEW to illustrate the impact on highways. So there are 10 controlled on-ramps, either reinforcement learning controlled or classic controllers. And we're using the real demand, but doing this light-duty vehicle and truck split according to this data. And as I mentioned, same backbone method. But this is for signals, this is for RAM meterings, because they operate in different dynamics and different kind of control intervals. So analytic results. This is the results for signal control, still comparing to Translead, but here we show that why previously I mentioned the robust agent could be a better, not could be, it's a better and more ideal alternative to these specialist style agents. So across the board, specialists can do better, but it still fails to generalize. But eMarlin robust agent, it can improve either travel time or emissions across different scenarios. And here we're also evaluating the emission profile across different pollutants. And the little light green is eMarlin specialist, and this, what is it? Purple blue is the eMarlin transformer robust agent. So on the highway of RAM meterings, after recalibration, the traffic demand with the tracks being considered, we're comparing to base case, which is without control. Alinea is a very standard RAM metering control algorithm. This is collaborated Alinea and variants to the Alinea, and this generalized version of eMarlin generalized towards this RAM metering scenario. And also, if we take a look across the board, total travel time, this collaborative version of Alinea is not dominating this standard Alinea, but our agent, which can reach an even better level of coordination, is doing significantly improvement on the total travel time. But also, if you look at the emission profile, it's like getting double the saving in some emission metrics. And this is a bar chart. So yeah, considering we don't have much time, this is more visual, is a better visualization. So the y-axis is the time axis, and x-axis is the space. So this represents the highway stretch from Ford Road to Highway 427. And without controlling, you see this heat map showing traffic is congested everywhere. And after applying the eBarney-X, because it coordinates from the very upstream to the very downstream, so it prevents the concatenated phenomena you may see in Alinea. And also the previous total travel time we calculated is the overall network travel time. So if you consider that we're pushing the vehicles to the what is that? Service road north and service road south, the studies suggest that it's saving the total travel time across the highway and the local. And similar findings for emissions. And thank you for your attention.
Thanks again, Xiaoyu. So the hypothesis here is that you fix traffic, you also help the environment. But we knew that, but we wanted to quantify it. And indeed, we're seeing like in the order of 10%, 12% reduction in emissions when you adaptively control traffic, whether it's on surface streets or on freeways. So with that, we reach